We talked a little bit about this, but an interesting thing with half-life is that unlike chemical reactions that we can speed up and slow down, we can't do anything about nuclear reactions, okay? Does anyone remember from our little presentation last time? What did he say, what do we do with the nuclear waste?
We bury it.
Yeah, we bury it, right? Because as of right now, it's gonna just decay at whatever rate it decays at. And we see that the shorter the half-life of something, the less stable it is. So we talked about like carbon-14, and remember what its half-life was from our lab?
5,730.
Yeah, there you go. So the 5,730 years, right? But then we talked about francium. Francium's half-life is like 1.6 seconds, right? Or like when livermorium was created 3 years ago or something like that, it literally has a half-life of like less than half a second. So it's like scientists made it, and then it was like gone, right? Because it is extremely unstable, okay? Looking at this graph, an important thing to be able to find on the graph is the half-life of your sample. Hopefully all of your Penny Lab graphs had this same shape. Did they all have the same shape, we hope? Yeah?
More or less.
Okay, because all half-life reactions will always have this similar shape, because it's always decreasing in the same increments of time, but it's always cutting in half. Okay? So the way in which you can find the half-life, the thing you got to be careful with is your units. Half-life is not the amount that's left. Half-life is how long it took for half of the sample to decay. So on your graph, if you want to draw this in on your notes just to remind you, what you do is you go to the halfway mark, and then you go down to the timeline. So for this particular sample, the half-life would be 1.3 billion years. Okay, the answer to a half-life is not 50%. Okay, because half-life is the time it takes to get to 50%. Another important thing about half-life is recognizing that even though half-life is constant, it's always 1.3 years, the decay of an individual atom is random. We couldn't predict which penny was going to decay when, but we could predict that about half of them would flip every round. Okay, so the two things we're going to learn how to calculate today or focus on is using half-life, is calculating the time that has passed and the amount that's remaining. Once again, the units are going to be key here in your problems, because if you focus on the wrong unit, you're going to find the wrong answer. If it's asking to find the amount and you give me an answer in years, it doesn't really make sense. Okay, so pay attention to your units because it will kind of guide you where to go. As we go through these problems as well, I'm going to kind of show you two different approaches you can take. A more mathematical using equations, or a more visual representation. I really don't care how you solve these problems as long as you understand them and get the right answer. Okay? One thing though for today is I do need to see work on every single problem. Even if for you, you can do it in your head, I need to see that your logic is there, even if it's simple, right? The work isn't a lot to show, but I need to see something. Recognize if you don't show me work, you will not get any credit for it, okay? All right, so let's look at this problem. So at midnight, we have a sample that contains 160 milligrams of some radioactive isotope. By 8 a.m., only 10 grams remains. So we want to know what is the half-life of the isotope. Okay, so the goal here is to find half-life. So my end unit, is this a unit of amount or a unit of time? Time, okay? So I'm going to do it visually here. So let's imagine I know I have 160 milligrams of my sample at 12 a.m. I know that this sample is going to break down over time to 10. And I know that happens at 8 a.m. So always a good first question to answer on these problems, if today you're like, oh, I'm stuck, I don't know where to go. a good first question to ask or answer is this. How many number of half-lives have passed? Or I'm going to call it, how many cuts has it gone through? So when we cut these things, the one thing that's going to mess you up is you got to remember it always is cutting in half, because that's why it's a half-life. Okay, don't ever cut them in thirds or fourths or eighths. Regardless of what the problem says, it's always cutting in half. So if I take 160 and I cut it in half, what do I get?
80.
80. Take 80, cut it in half. 40, cut it in half. 20, cut it in half. Ding, ding, ding. Okay, so how many cuts did it take to get to 10? 4. Everyone see that? Because we did 1 cut, 2 cut, 3 cut, 4 cut. So we did, this would be n is the variable you can use. That means cuts. So we've gone through 4 cuts or 4 half-lives. Is that my answer, though? No. What do we want to know?
The time.
The time. We want to know how long did each half-life take. So anyone have an idea of how we figure that out? Because what do we know about our overall time, Ben?
8 hours passed.
So we know that the total time was 8 hours. If we divide the total time by the cuts we made, it tells us that each cut took 2 hours. And that is your answer. This equation is the one written right above that box, right here, where if you take the total time and divide it by the number of cuts, you can find the half-life of something. Okay? Questions on that problem? All right, let's try another one. Okay, is this the next one on your paper? Iodine? Yeah? Okay. All right, so iodine 131 is used to treat thyroid cancer. The half-life of it is 8 days. 24 days ago, a doctor obtained a 48-gram sample. How many grams are now there are going to be left? So the first good thing to always start with, once again, is identify what is it that they give me. Okay? So what is this 8 days? What does that tell me? Good. So we can label that. So draw a little arrow from that 8. This is our half-life, which we symbolically can do as T with a subscript of a half. That means half-life. Okay? What is this 48 telling me? 48 grams. What does that tell me? Good. That's my original amount, right? So we symbolically represent that as capital A for amount, and then you do a little subscript I for initial. So the initial amount of the sample. Okay? And let's see, what else do we know? What's this 24?
This is how long it's been.
Good. This would be our total time. And our goal is to find what?
How many grams are left?
Good, our final amount, right? So the goal in the end is we want grams. All right, so I'm going to show you this one symbolically again, and then the next one we'll do with the equation you could use. Okay, so once again, a good first question to always ask is how many cuts is this going to go through? Okay, so I know I'm starting with 48 grams. Okay? What do we know is going to happen every 8 days?
It's going to go in half.
It's going to cut itself in half, right? So after 8 days, half of it will be left. Once again, if we take our total time of 24 days and divide it by our half-life of 8, we can find that there are going to be 3 cuts are going to happen here. Be careful here. A lot of people would see 3 and be like, oh, 48 divided by 3. No, because that means you're cutting it into thirds. Remember, this means it's cutting in half 3 times, right? So there's 1 cut, 2 cuts, 3 cuts, and there's your answer.
You could just divide 48 by 2 to whatever cut you have.
Good, and yes, that's what our equation will show us, how you can use an exponent to do the same thing. Questions on that? Once again, a good first thing to find, if it's not given to you, is the number of cuts. How many times is this thing going to get cut in half? Okay, so what Clark kind of pointed out to us is there's this equation we can use that if your number of cuts is really big, like let's say we're doing 12 cuts or something like that, that would be a lot for you to just keep, I mean, you could do it, but it would be quite the process. So this equation is really helpful when n is really big. You can actually use it whenever, but if it's easy for you to do this way, that's fine. But if your n is really big, then I'd recommend using it. Okay, so next to that equation, label what our different variables mean. How A of f is the final amount of the sample. A of I is the initial amount. And then n is the number of half-lives that have passed, or like I've been calling them, the cuts. So label our different variables, and then we'll try a problem using the equation. Everyone have that down? Okay, let's try this one. So, what does the problem give us? It says it has a half-life of 5 seconds. If we start with 25 grams, we want to know how many grams remain after 60. So, do I know my half-life?
Yes.
Yes, that would be our 5 seconds. Do I know my initial amount?
Yes, 25.
Good, that's our 25 grams. Do I know my final amount? No, that's what the question is asking, right? Do I know my total time?
Yes.
Yes.
There we go, 60 seconds. And then n, how could we figure out how many cuts it's going to go through?
Divide 5 into 60.
Take your total time and divide it by the half-life. So we know that it's going to go through 12 cuts in the end. All right, for a smiley face, don't say anything out loud. You're just going to nod your head yes or no. And it doesn't count if you just spin in circles and do both. Okay? So yes or no. Is it possible for A of f to be bigger than A of I? Just nod yes or no. Good. You're all saying no. So why? Nathan, what's wrong?
This isn't alchemy.
Cause say what?
This isn't alchemy.
It's not alchemy, right? Because what's happening to all the samples? They're decaying. They're getting cut in half. So this is a good logic check when you're doing these problems. If you got a really big number here, maybe you should backtrack and try it again because you probably did something wrong, right? It's always a good idea to do a logic check in the end. Does it make sense based off the question? Okay, if you said no, you can have a smiley face. All right, so now we're going to use the equation to help us solve this because of how big our n is. So our equation is, just a reminder, you take the initial and then you do 1/2 to the n. So our initial is 25, 1/2 to the 12th. So when you plug this in, do 1/2 to the 12th and then times it by 25. All right, so this question says, so we're talking about carbon 14. My problem is telling me that I have 6.25% of it remaining. So this would be my A of F. That's the final amount. Okay? We know that carbon 14's half-life, so this is my half-life, is 5,730 years. And then whenever a problem is using a percent, you always know the initial. What would the initial be? 100. Okay? So notice that if a problem is talking about percents, the initial is always 100. If it's talking about fractions, like it says I have like an 8 left, what would be the whole of a fraction? What would be your initial?
1.
Just 1. So just be aware on those questions. A lot of times they won't say your initial, but for cents, the initial is always 100. For a fraction, it's always 1. Okay? All right, so we want to know how many half-lives have passed. So rather than using our log rules, we're just going to think about this piece by piece. Okay? That if originally I'm starting with 100%, we just want to know how many times it's going to cut in half until we get to 6.25.
Which in this case, knowing the half-life is useless extra data.
For part A, you'll see that we'll use it in part B.
Part A.
But yeah, you're totally right, Nathan. Knowing that it's 5,730 years doesn't matter to us. We just want to know how many times it's going to cut, right? So take 100, cut it in half. What do we get?
50.
50. Right? And if the first ones you can do in your head. If it gets small and you can't, you just pull out your calculator to hit divide by 2, divide by 2. So 50, cut that in half. 25, cut that in half. We get 12.5, cut that in half. Ding, ding, ding. So now, how many times did this thing get cut in half? 4. Very good. You're counting the arrows, not the pieces.
So
yeah, Maddie.
You don't necessarily have to know how many cuts to do to find the answer. We just have to go until
We just,
get there.
yeah, because we know the beginning, we know the end, so just keep going until you get there.
Okay.
Yep. And then n equals 4 is our answer. Questions on that? So then, part B says if 4 half-lives have passed, how old is the specimen? So how would I know that now?
Times 4 by 5,700.
Yeah, we know that we did 4 cuts, and each cut is 5,730 years. So we just times 4 by the half-life, and we get what? 22,920?
Sorry.
No, you're good.
And there's our answer. Questions on that? Okay, for smiley face, let's have you try number 5 with your table buddies or on your own. And then we'll check it here together. Okay? Very similar idea to the one we just did. Okay, just to check this one, and then I'll set you loose on the homework. For part A on the notes, did we all get the answer of 8?
No.
Okay, good.
Okay.
Did we get 6?
Yes.
Good. Well, you should have got. Have a smiley face if you got that right. Which means on part B, it ends up being mathematically, it's 31.98. Technically, by sig figs, it does round up to 32.0. But as long as you mathematically are understanding it, that's what I care about right now. So, any general questions right now? Okay, on the homework,